Defoamers are a critical but often overlooked additive in coatings and adhesives formulations. They control foam during manufacturing, application, and curing, which otherwise can lead to defects like pinholes, craters, poor leveling, and reduced adhesion. Why foam forms in coatings and adhesives? High shear mixing during dispersion of pigments/fillers. Surfactants and wetting agents necessary for stability also stabilize foam. Waterborne systems are especially prone, but even solvent-borne adhesives/coatings can trap air. Foam formation steps: introduction and dispersion of gas or air, formation of bubbles, stabilization by dissolved amphiphilic molecules, rising of stabilized bubbles, penetration of the surface formation of the double layer. Foam is undesirable because it leads to surface defects, pinholes, craters, fish eyes, poor film properties, reduced gloss, weak adhesion, uneven thickness, processing issues, pump cavitation, incomplete mixing. Mechanism of defoamers. A defoamer is a surface-active agent that destroys foam after it has formed. An anti-foam agent is an additive that prevents foaming. The key to defoaming is to disrupt the surfactant-stabilized foam lamella. A defoamer works by entering the foam lamella bubble wall due to low surface tension, spreading and destabilizing the liquid film, causing rupture of the bubble, breaking foam. Key requirements: low surface tension, poor solubility in the medium, and controlled spreading. Types of defoamers in coatings and adhesives. Mineral oil-based defoamers. Traditional, economical. Often blended with hydrophobic silica. Use solvent-based adhesives, alkyd coatings. Limitation: can cause surface defects, cratering, poor recoatability. Silicone-based defoamers. Polydimethyl siloxane, PDMS, modified silicones, silicone oils with silica. Very efficient at low dosages. Applications: waterborne coatings, polyurethane adhesives, epoxies. Pros: strong and lasting defoaming. Cons: risk of surface defects if overdosed. Sometimes incompatibility. Polymer-based, non-silicone defoamers. Polyacrylates, polyethers, fluoropolymers. Better compatibility, lower defect risk. Applications: high-gloss coatings, pressure-sensitive adhesives, PSAs. Cons: often weaker than silicone defoamers. Silica-dispersed defoamers. Blend of oils, charms, waxes with hydrophobic silica. Provide long-lasting foam control. Common in waterborne coatings and sealants. Specialty/bio-based defoamers. Vegetable oil-based renewable polyols. Used in eco-friendly adhesives and coatings. Still under development for stability/performance. Selection factors. System type: waterborne, solvent-borne, UV curable. Viscosity: higher viscosity, stronger defoamer needed. Application method: spray coatings are more foam sensitive than brush/roll. Film requirements: high gloss versus matte, transparent versus pigmented. Compatibility: must disperse well but not dissolve completely. Practical considerations in formulation. Always start with low dosage, 0.1 to 0.5% by weight. Pre-dispersion versus post-addition. Some defoamers must be added early to control grind stage foam. Others at letdown to suppress application foam. Testing. Evaluate with drawdowns, foam cylinder tests, and application-specific trials. Balance defoaming power versus side effects, cratering, fish eyes, loss of clarity. Summary. Defoamers are essential additives in coatings and adhesives to suppress foam without harming film quality. Silicone-based defoamers dominate for waterborne systems. Polymer-based ones are chosen for high-gloss/clear coatings, and oil/silica-based are used in solvent-borne and economical systems. Current trends focus on low VOC, silicone-free, and bio-based defoamers for sustainable formulations.